Hey everyone, this is Sairam, and I'm working as a data engineer, and I'm working on distributed systems such as Kafka, Hadoop, Spark, and I develop ETL pipelines and real-time data-driven event systems. So today, what I'll be going through is the uh, Kafka design decisions and the important ones and uh, trade-offs between them. I'll be just going through each and every property in brief in this video. So these are the main properties that you can see on my screen with message durability, availability, message order, message uniqueness, consumer group offset, large message sizes, and then multi-region clusters. So in this video, I'll be explaining about all these points except the multi-region clusters that I'll cover in a separate video because that is a bit detailed and it will be best if I show you with a diagram and explain the internal moving parts as well. So, okay, I'll start with message durability. So basically what durability means is that when we send our message to the Kafka broker system to a producer, then the message should be present, that it should get lost in case if there is a network issue or if one of the brokers is down, etc. So how do you achieve this message durability? In our producer, we have this configuration called the ACKS AX configuration. We have three different types of configuration here. One is X is equal to 0, one is X is equal to 1, and one is X is equal to all. So these are the three different types of configuration for acknowledgement. So if you set your producer application with an access 0, then your Kafka producer client will send data or messages to the Kafka broker, and it doesn't expect a response back from the Kafka broker. So basically what this means is all the messages are getting pushed into the broker, but we have no idea whether the broker has received your message or not. So this configuration is not ideal for a durable system. Uh, but what advantage you get when your access equal to 0 is that you will get very good latency with this kind of configuration. So when you put your access 1, then uh, you, uh, then the broker will send an acknowledgement message back to the producer saying, hey, whatever message or data that you sent to me, I have received it. So in case if there is no confirmation from the broker, then the producer will try to resend the same message, making sure that the message stays in the broker. And if you put your x equal to all, then like for example, if you're having if you're sending a data to a topic A, then this topic A is having a replication factor of 3, which means 3 partitions will be present in your broker. So what this basically means is that when your message is being sent, then Kafka broker will receive the message and it will write into the leader partition. And then after it writes the message into its replication partitions, the remaining 2 partitions, then only it will send a response saying, hey, I received the message and I have copied the message to my other in-sync replicas as well. So even though X equal to all may affect your latency a little bit, this is the ideal setting for having a highly durable Kafka system based on your need. Next one, if you come to message availability, uh, we need a highly available system, right? Uh, like if your broker goes down, then in such a scenario also you need to preserve your messages. So if you want a system with high availability, then you have to have uh, more number of in-sync replicas, and your X configuration should be equal to all. And then you could increase your number of retries from 0 to any other number to ensure in case if even though there is a network failure or a broker failure, uh, the producer still attempts to retry sending those messages. And for message order, uh, some sensitive real-time applications like credit card transactions and banking transactions would is highly dependent on getting the order right. Like you don't want your credit and debit transactions to get mixed along the way, right? So in such a system, order is the highest priority of importance while considering designing your real-time application. So in such a case, uh, we have a property called enable idempotence in our Kafka producer. So what this basically does is that uh, it preserves your order and uniqueness as well, and it ensures that the messages written won't be duplicate. So it is like an exactly one semantics, if you can say, if I have to say it in short. So to achieve this, we have to enable idempotence in our producer property. We have to restrict our max in-flight requests to less than or equal to 5, and then we have to keep our number of retrieves for a message not equal to 0. So based on these properties, you will get your message order and uniqueness achieved. And the next property, consumer group offset property. So we can specify the auto offset reset property as none, earliest, or latest. So what this basically means is that when you set your consumer group offset property to none, then uh, if your consumer goes down, or if due to purging, or if the records get deleted in your broker system, and for example, if you are searching for an offset of 100 and it is not present in your broker and your configuration is none, then your consumer group will throw an error saying that whatever message you're trying to read is not available. So if your auto offset reset is earliest, then the consumer group will start reading messages from the earliest available offset that is present in your broker. And if you set your consumer offset to the latest as your property, then whatever last available data present for that particular topic partition, that will be read by the consumer group based on your offset property. And next one for large message sizes. So Kafka is not designed for consuming large message sizes, and Confluent recommends to keep your producer messages up to 1 MB and not more than that. So if you try to send large messages, then there will be some issues with your JVM tuning and garbage collection as well, and you will have some issues with your heap memory as well. So to process large messages, you can either break that large messages into record chunks and then have a unique ID for these chunks. I mean, like have a common ID for these chunks, and then send it in an exactly once orderly fashion using idempotence, and then reconstruct the message back by when you're reading it from the consumer. Or another way to look at this is that you could send the references through producers and consumers and store the actual large data in a separate directory like an S3 bucket or something, and then use your consumer reference to read the data from your S3 buckets. And for multi-region clusters, I'll be explaining that detail in another video shortly. So yeah.